Welcome to this session. Here we are going to learn about a new topic called asymptotic notations. And my name is Er.Sarabpreet Singh. I'm assistant professor in Amritsar College of Engineering and Technology. Now let's discuss what are asymptotic notations. So as you can see on the slide, that asymptotic notations are language that allow us to analyze an algorithm's running time by identifying its behavior as input size for the algorithm increase. What are these that we'll understand again after seeing these slides? These are some asymptotic notations, that is big O, big omega, and big theta. What are these? We'll just discuss in within few minutes. In big O, there is an equation called this equation fn is less than c of g of n, and where n is the input size. We'll also discuss this one is example. We'll come back to ppt just within few seconds. I'll have to start the camera. So I hope you can see the board now. Let me tell you that in order to solve any problem, if we want to, because design and analysis of algorithm is all about problems. So in order to solve any problem, in computer science, we generally write programs, as you already know. To solve problem, we write programs. So for writing programs, first of all, we'll draw a blueprint of it, that is called algorithm. Or we can say, before writing programs in any programming language, it is always better to write an informal description. Yes. So before writing this program, I'll write something that is very informal, and that is the description of program itself. And that helps us to write program, which also makes it easy for us to write programs. This is also known as algorithm. So we can see that for one problem, for any problem, let's say it's for searching an element or sorting a list of array, then it is called a problem. Now for one problem there could be multiple solutions. For one problem. Let's say there is a solution one. I will call it as A1, A2, A3, A4, A5, and so on. There could be multiple solutions. These solutions are first translated into algorithms. So that's why I've written A1, A2, A3, A4, and up to so on. So these algorithms, out of these algorithms, we need to find the best and efficient algorithm to represent this problem. So let's say it's A2 or any of these algorithms. So we need to find best algorithm. So how can we say this algorithm is best? We are assuming that A2 is best in this case, in this example. How can we say this algorithm is the best algorithm to solve this particular problem? So we can say if it takes lesser time than all other, then this one is the best. Lesser time and space, that is called time and space complexity. If it takes lesser time than all other, it is the efficient algorithm and the best algorithm out of all other possible algorithms. Okay. So in design and analysis of algorithm, it tells us how to design the algorithms in a faster way, or the algorithms that can take lesser time in computers to solve a particular problem. Now we will see there are some to analyze algorithms, we need its time and space complexity. And for analysis, there are some notations like these notations are called asymptotic notations. Asymptotic notations. So these notations are called asymptotic notations. This is our first topic name that we are going to cover today, asymptotic notations. So there are three types of asymptotic notations. These are some of there are other types as well, but these are some notations that we will be using in our subject. So first one is big O. Big O. This is called like this, big O. This is O notation. Okay. What is this? Let me tell you that. So first we'll draw a graph of it, and I'll tell you what is big O notation. So let's see, let's say this is the graph, and here at this axis we have time, and at this axis we have number of elements and time. Now if we can say that there is a this function f of n, it is nothing but rate of growth of time, rate of growth of time, or we can say it is time complexity of particular algorithm, time complexity of particular algorithm, rate of growth of time, or we can say it is time complexity. How to find out time complexity of particular algorithm, that we'll discuss in the next class, but this function is time complexity or rate of growth of time, or we can say what is rate of growth of time. It increases with the number of element increases. If we increase the number of elements in the problem, the rate of growth will also increase, because it will take more time. That is very obvious. If we increase the number of elements, the number of the time taken by algorithm to solve the problem will also increase. That is very obvious. Okay. Now what is big O in this? What is big O in this? This is not big O yet, but I'm going to explain you. What I'm trying to explain to you is what is big O notation, and how can we find out that. Now we can say again fn, f in f in fn, f is the function of n, and n is the size of input. So this is function of n, and n is the size of input. So we need to find out what is the worst case. What is the worst case in this case? So we need to find out that, or we can say what is the upper bound. What is the upper bound? So we'll say there is one more function called C of g of n that upper bounds this function. This means this fn cannot have a value greater than this function. Fn cannot have a value greater than this function. So this is the greatest value that f of n can have. Worst time that will taken by fn. Okay, the time taken by fn is not greater than this one. So I can say any function belongs to big O category on some particular n naught. What is n naught? I'll explain. On some n naught, I can say, or after finding fn, you can also find other function, that is c of g of n, c of g of n, after some input n naught, such that what is the condition? I can say that fn belongs to big O if Fn belongs to big O, or I can say Fn is equals to uh, big O of G of n. I can say that this is the upper bound of G of n only if f of n, this one, is less than or equals to C of G of n. C is some constant, nothing but some constant. Okay. So f of n is less than or equals to C of G of n, where C and n, or we can say C should be greater than 0. These are real numbers. C and n are real numbers. N, what is n in this case? N is, what is n in this case? N is also a real number, and C is also a real number, but n should be, or n naught should be greater than or equals to 1. Why 1? That I'll tell you. This n is nothing but number of elements. Let's say I want to sort 5 elements, so n will be 5. I want to solve 5 elements, sort 5 elements, sorting or searching in 5 elements, so n will be 5. That is input size. Okay, so input size cannot be 0. At least there should be one input, so that's why we have written for some n. So after n naught, n should be always greater than equals to 1. There should be at least one input for solving a problem. And we can say that problem belongs to big O condition. That is the worst case that you have been doing in the data structures. Like, what is the worst case of some algorithm? So what is the first worst case? This is the time complexity. I can say this time complexity is big O. Big O means the worst case. Is the worst case if we can find out this, what this, a value of C and value of G that satisfies this equation. This is the big O. So this is our big O notation. Let's see one example related to this one. At this side, I'm not going to erase this one. So this is relevant here. Now, let's see the example of big O for n. Big O, big O, big O notation. Then let's say if this is the function given to you, 3n plus 2. This is the f of n. This is the time complexity of some any algorithm. We don't know which algorithm, but this is the time complexity. F of n. F of n is 3n plus 2, and it is given. It is given in the question, and there is some function g of n, that is n. So we need to prove that what we want to prove is f of n is equals to big O of g of n. This is our question. This is our question. We want to prove that. Okay. So how can we prove that? For proving that, we need to prove that there exists some values of C and n naught after 1 that satisfies this condition. So we need to find out such values. So how can we find out? There is an hit and trial method. I'll tell you. So which function of n, will prove this? If I'll say 4 and I'll put n here. So instead of C, I've written 4 because I want to find out a greater value than this term, that is called 3n plus 2. I want to find out a greater value. What will be the greater value of 3n plus 2? It could be 4, it could be 5, it could be 6. But we need to find the tightest bond. So I have written that this value is this value will be greater than this value. So I have found the C, 4 here, and now I'll put one by one that satisfy this condition. If I'll put 1 here, and n's value is 1, this is n naught actually. This is nothing but n naught. So if I'll put n naughts value, that should be greater than or equals to 1. N naughts value should be greater than equals to 1. So I'll put 1 here. So if I'll check it, here we have 4 into 1, 4, and at this side we will have 3 plus 2, 5. So this is false. 5 is not less than 4. So we'll put the another value of n, that will be 2. That will be 2. So if we put 2, we'll get 8 on this side. 4 into 2 will be 8. And 2 plus 3, 6 plus 2 is 8. So this is true because this is less than or equals to this value. So 8 is equals to this value. So we can check if for 3 as well. It is true for 2. We can check it for 3 as well. So if I'll put 3 here, so 3 into 4 is 12. And 3 into 3 is 9, plus 2 will be 11. 3 into 3 is 9, and 9 plus 2 is 11. So this is false again. And if I'll put 4 again, 4 into 4 is 16, and 3 into 4 is, so it is true for previous value as well. Here we have 12 and here we have 11. If we put the value of n again 4, then we will have 3 into 4, 12 plus 2, 14, and then here we'll have 16. This satisfies the condition. So this means after by taking the value c and n not equals to 2, because for 1 it was false. N not equals to 2. After every value of 2, this condition will be true. So we can say this function is f of n is equals to big O of g of n, that is n, and this one is 3n plus 2. Now we'll check the next asymptotic notation, that is big omega. That is big omega. You have been calling it as the best case. That is not a best case actually. This is a best case, but how to prove that particular time complexity is a best case or not? So we'll see first the graph of it, and then we will see this is big omega. This is represented by this symbol. Okay. Now again we'll draw the graph. So here we have number of elements and time. So rate of growth of time is our time complexity, that is f of n. N is the number of inputs. N is the number of inputs. Now in the previous graph we have found the upper bound. Now we want to find the lower bound for the same function c of g of n. Any function that bounds it in a lower limit, that bounds this function, then that function is called the big omega of this. You can consider that minimum time taken by an algorithm to solve the problem. So that is this case. So we can only say that f of n, is omega of any other function g of n, only if we can satisfy this condition, that is, we'll reverse the sign here only. F of n is greater than equals to c of g of n. F of n is equals to greater than equals to c of g of n. So we can only say that this function is the best case or omega of this function if we can prove this. Or how can we prove this? We need to find such a c and such a n naught. And we already know that c and n are, c is greater than 0 and always greater than 0. Not, it cannot be equal to 0, and n naught is also greater than equals to 1. It could be equal to 1 or it could be greater than 1. Both are greater than 0. Okay. So this is the case. We'll see one example of this also. Now in the previous example, I forgot to mention one thing. Let's say this function was there, 3n plus 2, and we have said that this gn bounds it up in the upper limit. Upper bound is there. This function bounds this function, and upper limit is there, upper bound is there. So if this value, let's say 5 is the upper bound of this function, let's assume, automatically 6 will be proving this situation also. Okay, 6 will also be true for this case, and 7 will also be true for this case. If n satisfies this condition, n square will also satisfy this condition, n3 will also satisfy, n4 will also satisfy, n raised to power n will also satisfy. Anything bigger than that will satisfy this condition. But we need to find the tightest bound, tightest upper bound, that is n square. In the similar way, we need to find out the tightest lower bound, tightest lower bound. For finding that, we need to prove this one. The f of n is greater than equals to c of g of n. What is c? C is greater than 0 and n naught is greater than equals to 1. What is n naught here? This one is n naught. After some value of n, that is called n naught. If this condition is true, we can say this function lower bounds this function. Okay. Now we'll see the example. Again, we'll take the same example. Let's say 3n plus 2 and g of n equals to n. So we want to prove that f of n is equals to omega of g of n. This is our question again. We want to prove that this is the best case. So for proving that, in order to prove that, we will find such a c and such a n naught actually, that satisfies this condition. So let's write it down. 3n plus 2 is greater than equals to n. So I'll say if I put a value 1 here, c equals to 1, then also this satisfies this condition, and n is also equals to 1, n naught is also equals to 1. So if I put 1 here, so this will become 5, and this is greater than equals to 1. Okay, so this will become 5. If I put 2 here, then also it will be true. So 3 into 2 is 6, 6 plus 2 is 8, and here we have 2, 8 is greater than 2. So that in that case it is also true. Okay, so for c equals to 1 and n equals to n naught, this is the lower bound of this function. This is the best case of this function. We have found such a value of c and n naught. There may arise a question that we can find another example where this case is not satisfied. Okay, so we'll discuss that. Before going to next example, we can also find out. I want to tell you one more thing, that if I told you in the previous example, if a function is satisfied by n, it will also satisfied by anything bigger than n. In the case of big O, now this is satisfied by n, but this will not be satisfied by n square, because this is the lower bound, this one is the upper bound. This will be satisfied by anything lower than n. What is lower than n? What is lower than n? That is log n. Log n is a lower value than n. You can check it. If I put 10, it in the n it will be 10. But what is the value of log 10? That is 1. Okay. So what is lower than log n? That is log n. So anything lower than n will also satisfy this condition, but we need to find the tightest lower bound. So this n is satisfying this condition in lower bound. Now, in which case it will not satisfy? In which case it will not satisfy? So we'll see one example in which it will not satisfy. So if I write equation here, f of n equals to 3n plus 2, but gn equals to n square. Gn equals to n square. So I want to prove that f of n is equals to big omega of g of n. Can I prove that? Can I find such a c and n naught, value of n naught, that satisfies this condition? Here we need to find c. So I'll write 3n plus 2 greater than equals to c of n square. So what will be the value of c and n that satisfy this condition? So n could never be greater than n square. N could never be greater than n square. So we cannot prove that. So this statement is not true. This one is false. Okay. This one is false. Now we will see the next asymptotic notation. Next asymptotic notation, that is big theta. Big theta. Big theta. Oh, it's not too big. It's not that big. Okay. Big theta. So what is big theta now? I'll draw the graph again. Here, this is our f of n. Okay. This is our f of n, and there are both in this. Both upper bound and lower bound. Upper bound and lower bound. What is lower bound? We will name it as C1 G of n. What is upper bound? We will name it as C2 G of n. And after some value of n naught for all values of n. After some values of n naught for all values of n, this condition should be true. So such a function that bounds it in upper limit and lower limit, that is called big theta. So if I want to say f of n is bounded by g of n in big theta, then I have to prove that c1, this one, g of n is less than f of n, and this one, c2, is g of n. So this we need to prove to say that this is nothing but an average case. This is nothing but an average case. Here, you know, C1 and C2 should be greater than equals to 0, and n should be greater than equals to n naught, and n naught should be greater than equals to 1. Should be greater than equals to 1. So this is the case of big theta. We have already done both the examples. So we can say that this function f of n equals to 3n plus 2. This is the time complexity of some algorithm. And I want to say that what is the upper bound of what is the upper as well as lower bound of this function if g of n is equals to n. So I'll prove that both ways that we have already done, or you can do it again. This is our f of n. F of n is greater than c of g of n. This one is the lower bound. So we know n is the lower bound, and 1 is c equals to 1 and n equals n not equals to 1 for this. And if I'll say f of n plus 2 is less than equals to n, then we have c's value is 4, c's value is 4, and n naught's value was, what was the value of n naught? It was 2. So n is greater than equals to 2. So this is the average case. So what these asymptotic notations mean? What are these asymptotic notations again? Let me explain it to you again. As I've already told you, what are these three cases? Big O, big omega, and big theta. These are nothing but the worst case, the best case, and the average case. So if I'll say big O is worst case, if an algorithm is taking any time, it cannot take worse time than this. If it cannot take worse time than this. And what is the best case? If algorithm is taking less time, it cannot take more less time than this. That is the best case. Okay. Then what is the average case? What is the average case? Average case is only calculated in those cases where the best and worst case are same. Best and worst case are same. It is only applicable in those cases. Okay. So where best and worst case are same, no matter how many number of elements we provide, no matter what will be the output, always there will be a average case. Always there will be a same case of this best and worst case. I'll also explain you with example what are the best cases and what are the worst cases. Let's take an example of linear search. Or one more thing, we are not interested in best case. The programmers are not interested in best case. We are interested in worst case. Why? uh, how much time an algorithm or a program will take to solve a problem, and what is the worst time that in that time that problem could be solved. So it is the maximum time. So that's why we are interested in this worst case only. Now we'll take the example of linear search and what will be the best and worst cases and average case in this example. Let's say there are some elements in this array. The elements are, let's say, 5, 7, 2, 4, 1, 3, 9. What will be the best case in this case? If I want to find out x is element, so if I want to find out 5 and 5 is residing at very first position, so it will take only one time. This is the best case of this algorithm. If I'll apply a sequential search or a linear search one by one, I have to match this x. I will match this x with this one, then this one, and this one, and so on. This is called linear search. So what is the best case? If I want to find out the very first element in the search. And what will be the worst case? So best case, it can be written as like this, omega of 1. So it signifies this is the best case. Okay. Then what will be the worst case? In this case, there are how many elements there? 7 elements are there. So 7 will be the worst case. If I want to find out 9, that will be the case, worst case. Okay. But we're not sure how many elements will be there. So we'll write that there could be n elements. If we are searching in list of n elements, big O of n will be the worst case of this linear search. Big O of n will be the worst case of this linear search. Now, in the previous example, you have seen 3n plus 2. We have ignored the constants because this will be true for 4 of n. We have ignored the constants. Okay. So, if I'll find out the average theta case, the average case, that will be n by 2, or I can ignore this constant n by 2. Why to ignore this constant? Let's say there are hundreds and thousands and millions of values of n. Let's suppose it is this one, 10 raised to power 10,000. Okay, these many number of elements are there. If I divide this number by 2, then only it will not make much of the difference. So the average case is also same to the worst case. And I've told you this is not the relevant example for average case. Actually, average case only be considered in those cases where these two are same. Best and worst case are same. Now let's see the PPT, what we have written in the PPT again. So we are coming back to PPT again. Our topic is asymptotic notations that represent how an algorithm behaves, whether it is the best case or that this is how we do the analysis of any algorithm. Okay. So to analyze the algorithm, we need asymptotic notations like big O, big theta, and big omega. So this is how to identify the behavior of input size for the algorithm increase. So these are some cases of this. These are some cases of average case, and then worst case, and then best case. This is big omega, big O, and big theta. So these are the graphs. After n naught, if it satisfies all these conditions, we can find such a lower bound and upper bound of function in which we can satisfy this condition. Then we can say f of n is equals to theta of g of n. Okay. Then what is the worst case? If we can upper bound this function with this function, we can find such a c and n after some value of n naught. Then we can say this is the big O, and for big omega we can say this is the lower bound that we have already discussed in this video. And we have written here f of n is less than equal to c of g of n, where n is greater than equals to 0. And we can say, then only we can say f of n is big O of g of n. In a similar way, there is some example solved here that f of n is this, and question is f of n is order of g of n, and the next question is this g of n is this given is this log n, so we need to prove that. Okay. Then is a similar thing for big omega. The formula is given, f of n is greater than equal to c of n, where c is greater than 0 and n should also be greater than 0. Then only we can say this f of n belongs to omega of g of n. And then for theta, we need to find both cases. F of n is less than or equals to C of C1 of G of n, and is less than for C of 2 of G of n. That we have already discussed. And this is all about the PPTs. And that's it for today.